Alright guys, we're going to continue on with our polynomials notes, and this will be the part 2 video. We're going to finish up an example of using multiplicity to graph. We talked about multiplicity in our last set of notes, where if the multiplicity of a 0, based on how many times the factor shows up, really the degree, if you will, or the exponent attached to the factor, we know whether on the graph, our graph will bounce from that 0 or it will cross that 0. So we're going to see that here in this example. Okay, and then we'll get on to what we call the intermediate value theorem. It's an interesting theorem that is extremely common sense, but it has a lot of uses, especially when you get to calculus. So example 3 says, without a calculator, let's sketch the graph of this function. Well, the good thing for us is that they already factored it for us. We have this polynomial in factored form. The parent function, what should we be comparing this to? Well, that's kind of based on the degree, okay? So if we FOILed all this out, or you can just think of looking at the multiplicity, the highest exponent we would find on the x would be an x to the 5th power. Technically, there are x to the 3rds here, x squareds here. If we were to multiply all this together, the leading term would be an x to the 5th. So the parent function we're going to compare this to will be x to the 5th power. Our leading coefficient is positive. If it's written in factored form, really, you're checking what we like to call the a value. All right, that would be any constant that comes out in front of this function. Sorry, you couldn't see that for a second. The a value. If the a value is negative, our parent function that we'd consider, especially when looking at the end behavior, it would be a negative function. This has no number. You can think of it as an imaginary positive one there. All right, the x-intercepts, all right, also known as the zeros. Okay, let's figure out what they are, and let's also deal with the multiplicity of them, all in the same group here. So obviously we'll have a 0 of x equals 1, and the multiplicity of that 0 would be 3. Okay, we also have a 0 of negative 3, and the multiplicity of that 0 would be 2. Okay, and probably the most important parts of the multiplicity are whether it's even or odd. Okay, so here we're going to cross, here we're going to bounce. Okay, now we'll get that when we fill in our graph. Y-intercept, let's plug in 0 for x. 0 minus 1 to the 3rd times 0 plus 3 squared. We get negative 1 to the 3rd times 3 squared. Negative 1 times 9, our y-intercept is going to be down here at negative 9. Okay. The domain of any polynomial function will be negative infinity to positive infinity. We'll skip the range for just a second. Okay. Let's deal with the end behavior. Okay. This is a positive, odd-degreed polynomial. Odd degree, positive leading coefficient. So we have odd, we have positive, which means our end behavior will be as x approaches infinity, y will approach infinity. As x approaches negative infinity, y will approach negative infinity. And really, if you'd like to think of kind of the end behavior visually first, and then kind of write it in the terminology that we're looking for, that might be helpful. Okay? Starts low, ends high when it's odd positive. Okay? All this information should allow us to graph this pretty accurately. Okay? So we have a 1, 0 at negative 3. 1, 2, negative 3. I'm going to put a point there. A 0 at positive 1. At negative 9. 1, 2, 3, 4, 5, 6, 7, 8, negative 9. We have the y-intercept. We know the end behavior. We know that at negative 3 it will bounce. That makes a lot of sense. So we're going to come from down low, based on our end behavior. We're going to bounce at negative 3. Then we're going to come down here somewhere. Okay, we're not sure where this turning point's going to be. We're going to go through the y-intercept, and then we are going to cross at negative 1. Sorry, at positive 1. Okay, and this is how our graph is going to look. End behavior is correct. Number of zeros is correct. We're in good shape. All right. The range of this, well, let's think about this. Okay. On the previous example we had on the first part of the notes, we used our calculator to find the vertex. What do you guys think about this one? Is it needed? If we take a look at this graph, I think domain, obviously, every polynomial function will be negative infinity to infinity. Like, do we need to find this specific turning point to find the range of this graph? I don't think so. If it's going all the way down and all the way up, the range should be negative infinity to infinity as well. In fact, of any odd degree polynomial. Think about the end behavior of an odd degree polynomial. We're either starting low and ending high, or starting high, ending low. Okay, so we're going off to positive and negative infinity vertically in the y direction. So domain and range of an odd degree polynomial will always be all real numbers. Okay, let's move along to our intermediate value theorem. Now, before we do that, okay, the most important part of this really is taking our function and knowing how to work with it. The first example, we had to factor it. The second example, it was in factored form. That's probably the easiest that we could show you a problem and ask you to graph. Now, you guys know how to factor lots of things. You guys understand the relationship between zeros and other factors. You know how to factor by grouping. You know how to factor with the sum or difference of cubes. You know how to factor with the sum or the difference of squares. Okay, so there's a lot of different ways we could provide you with a polynomial function that factoring might be a beneficial strategy for you so that you can see where the zeros are, you can see what the multiplicity of each zero is, and then you can create a proper sketch of the graph, which we'll ask you to do a lot in this chapter. All right, intermediate value theorem. The words that we use to define this theorem, intermediate value, should make a lot of sense. So how about we do this? We're gonna kind of think of this abstractly before we give you kind of the math term here. All right, I'm gonna draw a little. We're gonna call this point A and point B. Okay. If I told you that point A and point B lied on a polynomial function. Okay, so I'm giving you that information. Both of these points lie on a polynomial function specifically. There is something that we should be able to conclude from that information about what might happen between points A and B. Okay? Point A is below the x-axis. Point B is above the x-axis. What must be true somewhere in between A and B if I tell you that this is a polynomial function? Pause, think if you'd like. What it should tell you is that since polynomial functions are smooth and continuous specifically, the continuous part is important, that somewhere between A and B, this polynomial function is going to cross the x-axis. How else could it get from below the x-axis to above the x-axis? If it's continuous, the only option is that somewhere between A and B, this graph is going to cross that axis, which means there's a zero between there. That's the intermediate value theorem. Okay? If P is a polynomial function, and P of A and P of B have opposite signs. Okay. This is exactly what I gave you here. I told you that between A and B was a polynomial function. We noticed that A is negative, B is positive, opposite signs. Then there exists at least one value C between A and B for which P of C equals 0. It's exactly what we just talked about. Okay? So, here we go. P of B, here's the x-axis. This is going to be P of A. Here's A. Here's B. Okay. If P of A and P of B have opposite signs, well, let's even switch them from our little example. Actually, we can't because we already wrote this down. Here's P of A, here's B of B. Then in between here, in between A and B, there is some value C for which P of C would lie right on this axis. P of C would equal 0. Somewhere along it. Here, 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 we can put it randomly. At some point, this polynomial function has to cross the x-axis. There has to be one or more zeros between A and B. Example 4 says, using the intermediate value theorem, show that the function f of x equals x minus 1 to the third has a 0 on the interval -3 to 2. Okay, what this is asking, use the theorem we just showed, the logic here, to prove to somebody that in between x equals -3 and x equals 2, there has to be a 0 somewhere. Let's do it. So let's find f of -3, and let's find f of 2, and I'm assuming they're going to have opposite signs. If they don't, we can't use the intermediate value theorem. So -3 minus 1 to the third, that's -4 to the third, that's -64. F of 2, that's 2 minus 1 to the third, 1 to the third, that's 1. Okay? Since f of -3 and f of 2 have opposite signs, there must be a 0 between x equals -3 and x equals 2. There we go. Pretty simple. And that wraps up part 2 of our polynomials notes.